So, derivatives. Here's our question. At the drag strip in Cedar Falls, a driver was clocked as finishing the 4th mile track in 4.02 seconds. What's the difference between these two statements? The dragster averaged 224 miles per hour, and they reached a top speed of 240. What's the difference between those two statements? Which one is? This is a peak? Oh.
Yeah.
Okay. This is a peak. Also, this is a speed at a single point, right? There, yeah. Because the peak is a single point. And how is that different than number one?
That's like the average speed over the whole thing. Yeah.
Average, we used multiple points to find this. All right, so the key word is number one is an average. Number two is at a single point. Do you know our word for at a single point? Instantaneous. So if you say that a dragster reached a top speed of 240 miles per hour, that is an instantaneous speed, or a speed at a single point. All right. Second question, what is rate of change? Definitely has something to do with slope. Slope and rate of change can be interchangeable words. All right, does anybody have anything else to add, or is slope good? That's good? Okay. Okay, how about this one? Ooh, this one's fun. Okay, I learned this year that the PACER test is still a thing. But my understanding of a PACER test is different than what it actually is. It's actually much harder than what we're going to look at in here. So I thought that you run up and then you get 30 seconds of rest and then you go back, you get to rest, but you don't actually get that long to rest each time. It just depends on how fast you finish, right? Huh.
Yeah, if we did that way.
You did it this way?
You would never get out. So cross country people would be going for
Okay, so let's see. In this table, some data. Let's graph this data to the right. So let's go ahead and graph this. Hey, class, PACER test. Is it the long way? Short way on gym?
Short way.
How far is that?
It's a volleyball court.
No, it's definitely not 100 yards. Like,
I don't know what the length of the
I
I'll
think
look
it's
it up.
20. I think it's 20 because she did the 15-meter PACER test on us instead of like 20 or 25.
25 feet?
It's in yards.
No,
20 yards?
meters.
20 meters?
Yeah.
Aren't yards in meters? Like,
I don't know. We run the
20
volleyball
meters.
court. What's the length of a
20
volleyball
meters, I
court?
got it right.
20 meters. Okay, so that means we're running from 0 meters to 20 meters.
one of those days, you just like run a whole football field. 30 seconds.
All right, y'all. And so what's going to go on the x-axis? Time. What unit of measurement is our time in? Seconds. Cool. So we run 20 meters. The first time, how long does that take us? 33 seconds. Maybe I'll just increment these in groups of 30 seconds. So we'll go 30 to 60 to 90 seconds, and then 120, 150, 180, 210 and 240 will be plenty. And it takes us 33 seconds to run the first 20 meters. So we'll go ahead and plot that point up here. Let's say we run at a constant speed. All right. And then what happens for the next 30 seconds? Nothing. We rest. So how do I draw that? It's a straight line, straight across for another 30 seconds. So I'm just going to write this is at 33 seconds, and then this one will be at 63 seconds. And then what happens? We run back. How long does that take us? No, yeah, it takes us 29 seconds.
Oh.
The next one takes us 30 seconds. So let's see, 63 plus 29. That'll be 92 seconds, right? So after a total of 92 seconds, we've gone back to our starting point. And then what happens for the next 30 seconds?
Nothing.
We chill. You wish the pacer test was like this?
No. I thought about it, and then I was like, no, that would take like an
You would
hour.
stay in forever.
All right, well, what happens next? We go back, and this takes 38 seconds. So that'll be 122 plus 38. That brings us all the way to 160, right? Yeah. So this will be time is 160. Cool, and then we chill for 30 seconds, brings us to 190. And we go back down, that takes us 43 seconds. Which brings us to a total of 200, wait, how many? 43 seconds. We got tired. So that's a time of 2:33, right? All right, now the question, what's the student's average pace for the first minute? How do we find the average pace or the average speed? How do you calculate speed?
Distance over time.
Distance over time. Well, how far do they go from 0 to 60 seconds?
20 meters.
They only go 20 meters. And it takes them 60 seconds. That means they go a third of a meter per second. Sadie says that's not very fast.
For the second, I think.
About.
My stride walking is
So why is this so low?
This is big stuff.
Because this is most of this time we're resting, right? Yeah, so average speed just tells us like over a time period what was our average pace, but that doesn't take into account, like what if we sprinted for 20 seconds and then just rested? All right, cool. Do we have questions?
No.
Not yet. Do you need to flip the page?
Yeah.
Okay, this one. We have a free falling object. What does it mean for an object to be free falling? Just falling. You just drop it. You're not dropping it through water or anything. Just falling. Okay, where time is in meters. Nope. Where the function is in meters. T is time in seconds. Answer the following questions. What is the average rate of change of the object from 0 to 2 seconds?
About 30.
0 to 2 seconds. Y'all, remember that average rate of change is really just the slope of the line between those points.
Over the 2 seconds. 20. Divided by 10 could be 2.
Say this louder.
So it goes 20 meters over 2 seconds.
But we're going down because we're falling. So negative 20 meters
Yes.
over the course of 2 seconds.
Yes.
So this is about negative 10. What's the label?
Meters per second.
Yeah, we fall at a rate of negative 10 meters per second. This direction just means that we're falling, we're going down, going downwards. Cool, not too bad. How about the average rate of change of the object from 1 to 3 seconds?
So it goes from 45.
So it goes from 45 to 5, so that was a distance change of negative 40 meters. And then per 2 seconds again. So this rate of change is a negative 20. An average rate of change of negative 20 meters per second. All right. And then the average rate of change of the object from 0 seconds to when it hits the ground.
That would be 50,
Yep, we go 50.
3.2.
Takes us a whole 3.2 seconds. And only negative 50. We fall 50 feet or 50 meters. All right, what is negative 50 divided by 3.2? Negative 15.6. Are we good? Okay. Probably me and my cord. Meters per second, right? This is like a velocity. Traveling downwards at a speed of 15.625 meters per second. What questions do you have at the moment? Is this all kind of review for you? Yeah?
I don't check this.
Okay, how about a math example, more abstract? Given the function f of x equals x squared, what's the average rate of change over the interval 1 to 2? This means from x equals 1 to x equals 2. That's what that means. Oh, teacher's already finding that.
Wait, what?
Didn't you just say the answer?
It goes up 3.
Yeah, so the average rate of change is really just the slope between these 2 points, which is change in y over change in x, which is, I'll write it out, 4 minus 1 over 2 minus 1, which is 3. This means that the average slope between the points 1 and 2 is 3. And now we're going to start getting into the idea of a derivative, y'all, because a derivative is the slope of a line at a certain point. So not an average, just what is the slope at a single point. So let's do these next intervals real quick. So do you see all these intervals down here? 1 to 1.5, 1 to 1.1, and then 1 to 1.01. Do you see how that interval is getting smaller and smaller and smaller? We're getting closer and closer to 1. Let's see what happens to the slope. Do you have any predictions? I think they'll be the closest. Yeah, they'll approach a number. Okay. So let's see. This first one, when x is 1, what's y?
1.
When x is 1.5, what's y? What's 1.5 squared?
2.5.
2.25, you mean?
Yeah.
Because 15 squared is 225. Okay, these are the 2 points. What's the slope between these 2 points? Do you understand the question?
Yeah,
Oh, okay. Okay, we're just working. Okay.
we would take 2.5 minus 1 over 1.5 minus 1.
So we take 2.25 minus 1 all over 1.5 minus 1. And what do we get when we do that? 1.25 over 0.5, which is 2.5. Okay, so that's the slope between that interval. How about the slope between 1 and 1.1? Can you just tell me what's the slope between x equals 1 and x equals 1.1? Or do you need me, should we set up the points maybe? The points are 1, 1, and 1.1 and 121, so 1.21. What's the slope between those 2 points?
$2.1.
2.1. How about the average rate of change between x equals 1 and x equals 1.01? Do you have any predictions? This one is 2.01 if you were to calculate it. What do you notice about these slopes as our interval gets smaller and smaller? The slope gets closer and closer to 2 as our interval gets closer and closer to just being at a single point in that when that point is at 1. So as the interval moves closer to 1 to 1, which is a single point, this rate is considered instantaneous. This is our instantaneous rate of change. That's kind of a lot of work to find the instantaneous rate of change, isn't it? It's just kind of estimating it using intervals that get smaller and smaller. Do you think there's maybe an easier way to do this? Hope so. What questions do we have at the moment?
So how come every slope we got, if you like added the 2 points together, that would get the slope? Is that just like a coincidence for this problem?
That's a good question. Let me think about it. Is that a coincidence? Huh. Yeah, that is a coincidence. Do you understand what TJ is saying? Yeah. That has to do with that our specific function was x squared. Hold up. What if it were 2x squared? Yeah. Yeah, that is actually a coincidence, but I do like the pattern finding there, though. Yeah.
That's why I thought.
Yeah. Huh. Yeah, wow. Good observation. Anything else? Okay, flip the page if you're there. Or do you have anything more at the end of this page? No? Mine got all goofy compared to yours. Okay, so this is actually about this graph, y equals x squared. So estimate the instantaneous rate of change at 1 second. We already did that, didn't we? Yeah, that's what all this stuff is. So the answer to 1 is 2. And now, estimate the instantaneous rate of change at 2 seconds. We'll do it for 2, and then we'll just eyeball it for 3. How about that? So for 2, when we get closer and closer to 2, what do you want our rate or our interval to be? From 2 to what? 2.5? 2.5? So we'll find the slope between that interval, and then we'll just go 2 and 2.1, we'll say. So let's see. If x is 2, what's y? 2 squared, so that's 4. So our points are 2, 4, and 2.5. What's 2.5 squared? It's 25 squared. 625? So 6.25. So there are 2 points for that one. This point will be 2, 4. And I don't know what 21 squared is. 4.41? Okay. Cool, so go ahead and find the slope between each set of points. And we'll see if we can estimate this instantaneous rate of change as their interval gets smaller. Oh, sorry. Yeah, my bad. This should be 2.1, comma, 4.41. All right, shout it out when you get those slopes.
For the first one, I got 4.5.
The first one is 4.5. That's our slope. Okay. How about for the second one? Did anybody different get that?
And then the second one, I got 4.1.
4.1. If you could take a guess, what does our rate of change appear to be approaching as we get closer and closer to just a 2, 2 interval? 4. So this one does approach 4. Predict at 4 seconds. What do you think our slope will approach? 8. You are actually right. Right? 2 times 4? Yep.
Is it the y x? Oh, the negative. Hey, Joshua.
Yes. Yes, I guess I didn't. I never specified that the slope is the change in y over change in x. So it'll be like your first y minus your second y over your first x minus your second x. Yeah, sorry for kind of glossing over that. Do we have any other questions at the moment? Do we understand the difference between an average rate of change and an instantaneous rate of change? And how it's all just dealing with slope and whether or not that's like a secant line or the tangent line? Maybe? All right, you ready for this formal definition?
So what's this, another term for instantaneous rate of change?
Oh, sorry, thank you. Another term for instantaneous rate of change is derivative. This is what we'll be learning about for the next, like, 2 months.
Wait, so I have a question.
Okay, what's your question?
For the, 2 comma 4, or not 2 comma 4, but the 2 comma 2.5, where do we get the 2?
This?
Yeah.
Right here? Why are we using 2?
Yeah.
We're looking for the rate of change at 2 seconds.
Yeah.
So I just chose to start with 2 going to 2.5 because that's an interval of 0.5. And then I chose to make that interval smaller between 2 and 2.1. But you could have also done 1.5 and 2. You're just trying to find the intervals that get closer and closer to 2.
And then how did you get the? So then for the second number, you just. took
And these are
that,
both x values.
Squared it.
Yeah, so then if this x value is 2, then 2 squared is 4. That's how you find the y value. For this x value, we had 2.5. So to find the y value, we took 2.5 squared, which is 6.25. Good questions. Any other questions from anybody? All right. Let's talk about the formal definition of a derivative so you can kind of understand what all this means. Okay, so remember that the derivative is just the instantaneous rate of change, or we're trying to look for the slope of the line tangent to the curve, like at a single point. So, for example, on this line, when we were trying to find the slope of the graph at 1, that's just the slope of the line tangent to this graph. And that's what a derivative is. It's the slope of this line tangent to the curve at a single point. So now we're going to talk about finding an easier way to calculate the derivative instead of just kind of estimating by making intervals smaller and smaller. Yeah? And here's the big idea. If you're trying to find the derivative at a point x, you're going to say, okay, at x, my y value is f of x. F of x is like y, remember? And then to find the slope, you need like what Alexa was just talking about, and Megan and Sadie. You need, like your y2 minus your y1 over your x2 minus your x1. And this is your slope, right? So to find the slope, you need 2 points, right? But we're going to talk about finding the slope at a single point, which means we're going to use limits. So we're going to find the slope between 2 points, but then say, well, as we get closer and closer to the point, what's the slope? So we're going to find our point x. That's where we're looking for the slope of the line at point x. And we're going to say, okay, well, x plus h will be somewhere over here. We're creating an interval. And that y value will be f of x plus h, whatever x plus h is. And then the slope between these 2 points is your second y value, which is f of x plus h, which shows up right here, minus your other y value, which is f of x, which shows up right here, all over x2 and x1. So this is like your x2, your x1, y2, and y1. Okay, but you see how this is just an h in the denominator? That's weird, right? Well, our x2 is really just x plus h, isn't it? That's this guy. And then our x is just, our x1 is just x, so the x is reduced to 0, or they simplify to 0. And you're just left with an h, and that's where this comes from. You're saying, well, cool, that's the slope between any 2 points on a graph. I've known how to do that since I was in 8th grade. And now do you see this limit sign? This means we are going to bring these points closer and closer together. In other words, we're going to say as h gets closer and closer to 0. So as we make this h value smaller and smaller, we will approach the slope at x itself. So it's like we're bringing these 2 points closer and closer together until you just are approaching x. And that's why we have the limit as h approaches 0. And that's what the derivative is. This is the sign for a derivative. That's the symbol. We're saying the derivative is the slope between this point and this point, but as these points get closer and closer together, so it's just trying to find the slope at the single point, and that's like a formula we can use to find that. So what we're really doing is finding an equation to find the derivative. Finding an equation of the derivative. Does this make any sense? A little bit? So we'll do some examples and then maybe that'll clear up some questions too. So this gives us the general equation that will allow us to find the slope of a line tangent to a curve at a given point. Throw a star by this sentence. That's the key. That is what a derivative is. The slope of the line tangent to the curve. Can you tell me the next blank? This equation allows us to find the blank rate of change. Instantaneous at a single point. Instantaneous. We've been working with average rate of change, but now we're going to move into instantaneous rate of change, which are derivatives. All right, cool. Oh, also, is this the last thing on your page?
No.
Okay, well, okay. Just a quick language note. The word derivative is a noun. Like you can find the derivative of a function. Oh, I guess I have that written, which is the slope of the line at a given point. And this process is called differentiating, which is a verb. So you can differentiate a function, which means find its derivative. Yeah. And you know these words, just maybe not in the math context, right? Okay, cool. Differentiate the function, aka find its derivative. Actually, can we do a simpler one just to start out? You wanna? Do you have any room on your papers, or do you just want to watch? Okay. Let's do the function f of x. Give me your favorite linear function. 6x? No, let's just do 6x. Okay. Our derivative formula, dy dx, that's a derivative symbol, is the limit as h approaches 0 of f of x plus h minus f of x, the change in y over the change in x, which is actually just h. For us, we know what f of x is, right? What is it? Don't overthink it. F of x is just 6x, right? What is f of x plus h? Yeah, that just means we replace each x with x plus h. Cool. Whoa. Okay, let's distribute, and then for this process, you will always have terms cancel out. So the limit as h approaches 0 equals the derivative of, let's distribute, what's 6 times x? 6x plus 6h minus 6x. Wow, do you already see things that reduce to 0? I do too. So this is the limit as h approaches 0 of this negative 6x and this positive 6x simplified to 0, right? So what is 6h divided by h? These h's will reduce to 1. So this is just the limit as h approaches 0 of just a plain old 6. What's that? Do you see any h's? So we can't plug 0 in for anything, so this is just 6. Which means this is the slope of the line tangent to the line 6x at any point. Y'all, we just found the slope of this line, but you could have told me that right at the beginning, couldn't you? So maybe derivatives are a little boring with linear equations, huh? That's okay, though?
I like boring.
So if it was 6x plus 2, would it still come out to 6?
It would have still come out to 6. Because you would have...
6 plus 1 million instead of 6.
What's the question?
Oh, okay.
Yes, sir. I didn't cross those out. The h over h reduces to 1. Cool. What other questions do we have? You ready to try a harder one? X squared. This is on your papers, right? Okay. Maybe can you guide me? Or do you want to try this on your own, or do you want to guide me through it? You want to guide me through it? Just in case. The derivative is the limit as h approaches 0 of what? You tell me. Yeah. What's f of x plus h first? Yeah. This means we replace that x with an x plus h. This is actually just x plus h, quantity squared. That's what f of x plus h really is.
We square the h.
Yep, we square that whole x plus h term. So this is really x plus h squared. That's f of x plus h. What's f of x? So we'll write minus x squared, right? And all over what? All over h. So this is the limit as h approaches 0 of, let's simplify, and then things will cancel out. What's x plus h squared? X squared plus, yes, 2xh, don't forget about that middle term, plus h squared, and then minus x squared, don't forget about that term, all over h. The 2x squared on the top simplify to 0, so we can cross those out. This is really just the limit as h approaches 0 of 2xh plus h squared all over h. Can we find this limit yet? What happens if we plug in 0 for h? We still divide by 0, so we need to simplify this a little bit farther. Can we remove an h? Do you mean factor out an h? Yeah. Cause let's factor an h out of the numerator. This is the limit as h approaches 0 of h times, what if we factor out an h? So we get h times 2x plus h all over h. Now what do you notice? There's an h on top and an h on bottom. So what can we do? They cancel, they reduce to 1. So this means we have the limit. Did you run out of room too?
No, I'm still on.
As h approaches 0 of 2x plus h. And now can we plug in 0 for h to find this limit? Yeah, let's plug in h is 0. What do we get? A flat old 2x, which is an equation of the derivative, an equation of the slope of this line at any point.
So 2x is the derivative.
Mm-hmm. What questions do we have? You feeling okay about it? Maybe?
So we just get rid of h because we put 0 in for that h.
Yeah, because when we find the limit, that means if you can just plug in the value for h, then that, and you can find the limit, then that's what you do. So we plugged in 0 for h, and we got 2x plus 0, which is just 2x.
Oh, so okay, so up here, we were doing like the 1 second, 2 second.
When are we doing what?
Factoring by 2. I get it now. Never mind.
Yes. Hey, Alexa, can you say what you found? Okay, so Alexa's talking about these slopes that we estimated.
Yeah, so we're just putting them in 2x equation.
So we know that the derivative of this x squared, which is where all this problem is all about, is y equals x squared. That's what this is. So we know the derivative is at 2x. So when x is 1, what was the derivative? Or what was the slope? When x was 1, the slope was 2. When x was 2, what was the slope? Huh, because 2 times 2, plug in 2 for x, that equals 4. And then your prediction, 2 times 4, if x is 4, the slope was 8. Pretty cool, huh? All right. Yeah, really good observation. Anything else we notice or wonder or have questions about? Shall we talk about some of the notation that you'll see going forward? So we've used dy dx.
About the problem, what is the value of the derivative as x equals 1?
Oh, sorry, I missed that because mine is cut off, huh?
So do you just put 1.5 in for x?
We put 1.5 in for x. So I'm sorry, can I write this in the margins and you can write that in the space that I gave you? Okay, so I'll just write this here. When x equals 1.5, the derivative is 2 times 1.5, which is 3. And then what does this mean?
Slope of the line is 3.
So the slope of the line tangent to the curve at x equals 1.5 is 3. Can I write that here instead?
Are most of the derivatives we're gonna be working on, like f of x equals x squared?
Yeah, you won't have anything too complicated right now. Like I want to give you a cubed or anything to do with this with, but next week we'll find there are patterns. You'll notice some patterns and we'll find some shortcuts that you can use that you don't have to use this method every single time going forward. Okay, so the derivative is 2 times 1.5, which is 3, right? This means the slope of the line tangent to the curve at x equals 1.5 is 3. That's what that 3 means. The slope of the line tangent to the curve at x equals 1.5 is 3. Or you can say the instantaneous rate of change at 1.5 is 3.
Oh.
All right. Does anybody still need this? Okay. All right, let's talk some vocab. And then maybe call it a day. Sound good? These are all of the ways that we will denote derivative going forward. Personally, I'm partial to this one. You'll see a lot of that from me, or this one. But yeah, so you say this y prime. That means derivative. And our friend Lagrange came up with this. Lagrange was a French mathematician.
I've heard of him.
Yeah?
Not sure why, not sure, but I've heard of him.
Nice. F prime of x is this one. Everybody say f prime of x.
F prime of x.
You can also say the derivative of f. Yeah, Lagrange came up with that one too. And then Leibniz, our calculus European guy, said dy dx. This is the derivative of y, of an equation y, with respect to x, which just means x is your independent variable. Yeah, that's all that means. And then Leibniz also said, okay, well, we can also use df dx. Where do you think that f comes from?
Hunter Worthen, please stop by the office before leaving today. Hunter Worthen. Also a reminder that school pictures are still in the media center. If anybody wants to pick one up, pick theirs up after school. And there are volleyball pictures here in the office. If you've not picked yours up, please stop by before leaving.
Okay, hang on now. Let's finish this. df dx. Where's the f come from? Take a guess. F of x, like a function, right? Yeah. And then this one literally says d dx of f of x. Actually, I really like this one too. d dx of f of x. That's how you would say that. And then y dot supposedly is used a lot in physics, developed by Newton. But these are all of the different ways that you can represent a derivative. All right, and we'll finish these notes tomorrow. Sound good? All right.
Can I go to the office to go